But I would still wait till after the hour.
Yep.
Okay.
Let me see.
But we'll stop making jokes about this. What was your question?
Can we see when people?
Yeah, so if you get the meeting controls back, so one thing, well, you can, if you switch out of presenting, you can have it so that the chat's on one side and participants are on one side. Or you can, it actually shows up both sides, the chat here and participants here. Yeah.
Let me actually put the chat on always, because then it will be easier to see. But you're monitoring the chat too.
I am not.
Not okay.
If you want, I can move over.
No, no. That's can they see the chat too? Or
they can see the chat.
Okay.
You should ask one of them too.
Yeah, if someone or all of you can also monitor the chat, just in case I'm missing something, then we can elevate the question. Okay. Good to go?
Good to go. Let's do it.
Are we ready? We're ready. Okay. So good morning, good afternoon, good evening, depending on where in the world you are. I'm Julia Koschinsky. I'm the Executive Director of the Center for Spatial Data Science at the University of Chicago. And I organized this panel because we had a problem. And it turns out the people on this panel had been working on solutions to this problem for several years. And so what's this problem? The problem is that students often have incredible technical skills in computation and statistics, but still have trouble to critically solve problems with data. And so examples that we were discussing earlier with the panelists are, for instance, that students can derive, all the proofs, but still fall into bias pitfalls when they actually have to analyze data. Or they think that the random forest modeling that they've just spent so much time learning is the solution to all of the data problems that they are faced with. And so as I was talking more and more with others about this, it turns out that this was actually a problem of general interest and not just ours. And then as educators, the question is, okay, how do we go and fix this? And so I've been looking for approaches that teach data science with scientific thinking or other ways to critically engage students with how they're analyzing data. And in our own work, we're now starting to explore how to better integrate scientific reasoning concepts like explanation, refutation, and iteration as the scaffolding for how to explore spatial data. And Data 8 also is a great example of not just teaching programming, but also computational thinking and statistical inference with real-world data. And so a shout out here to Mahmoud Harding, who was also at this workshop from the math department at North Carolina School of Science and Mathematics, where they're doing incredible work in this area. And so let me find out here. And so the idea, of this panel was to bring together people who've been working on solutions to engage students critically with how they are analyzing data. And so I'd like to introduce you to 4 panelists who've done fantastically inspiring work in this area. They come from natural and social sciences, physics, political science, math, and psychology. And first is Aditya Ranganathan, who's a PhD candidate in applied physics at Harvard. And he's representing the Sense and Sensibility and Science course, which has been co-taught by a physicist, a philosopher, and a psychologist at Berkeley for over 10 years. And so this course recognizes that as humans, we're prone to fool ourselves and teaches scientific reasoning as a way out, including for democratic decision-making. And so next is Anthony Fowler. He's a professor at the Harris School of Public Policy at the University of Chicago. And Anthony has co-authored a book and course on thinking clearly with data, which teaches statistics in R with a strong focus on critical thinking and biases. And these courses are undergrad or grad courses. And Niki Cotton represents high schools as a math teacher at the Noble Network of Charter Schools in Chicago. And she's a curriculum writer for Skew the Script. And this is a new open curriculum that makes math relevant to students by focusing on real world problems and data. And then last but not least, Daniel Lakens is an associate professor in the Department of Human Technology Interaction at the Technical University Eindhoven in the Netherlands. Daniel developed 2 large Coursera courses, Improving Your Statistical Inferences and Improving Your Statistical Questions, which focus on statistical pitfalls and how to get out of them. And this work was motivated by addressing the reproducibility crisis in psychology. Okay, so here's the schedule. First, each of the 4 panelists will do their own intros and explain what pain points got them started, who their curriculum is for, and how their courses differ from the typical statistics and computation class. Then we'll discuss some questions that we were interested in answering. And then finally, we'll open it up to Q&A for the audience. And you can always use the chat for the questions that you have. We'll monitor that. And if you want to actually say something, in person, we'll unmute you so that you can use that instead of the chat. We'll use for the answering the questions, the order of the pictures here. And so Aditya, if you can kick us off with the intros.
Absolutely. First of all, thank you, Julia, for that lovely intro, and thank you all for being here. As you might have guessed by now, my name is Aditya Ranganathan, and Julia, do you mind if I take over the screen sharing for a moment? I put together a few slides. All right, so let me know if you can't see this, but my name is Aditya Ranganathan, and I wanted to talk to you a little bit about a course that we've been developing at Berkeley, which is now also extended to other universities, including Harvard and UC Irvine and possibly Chicago in the near future, called Sense and Sensibility in Science. And broadly, this was a course that was founded in 2013 by Saul Perlmutter, who's a professor of physics, John Campbell from philosophy, and Rob McCoon from public policy and psychology, to address a lot of the crises which in 2013 seemed like a big deal. I mean, I think we can argue maybe now that the crises we're facing today are even bigger, and therefore this sort of material is even more important. But at the time, I think we were interested in things like the debt ceiling and climate change as a perennial problem, and I think it was motivated by thinking about two aspects. So the first aspect is, of course, to say, well, what are the tools that one might learn, let's say as a graduate student in the sciences, that could have an impact on the way we think about political problems or social decision making? And of course, the second part of that is if you go to a faculty meeting in physics, you'll see a lot of decisions get made by people banging on tables. So clearly it's not enough to have the sort of the scientific training if that's not combined with some sort of efficient group decision-making process. And so we started this course on scientific thinking or scientific-style critical thinking to address a lot of these issues. And of course, this is for those of you who are from Berkeley or in the Berkeley audience. I highly encourage you to check out the course. Happy to talk more about that as well. It's listed as LNS22 and it will be taught again in the spring. But I think there's also a really important piece of this sort of material in the context of data science. And it's broadly, I think, something that Julia already mentioned, and maybe everyone here already knows, so I'll be quick, but it seems like it's fair to say that data informs almost every big decision today. And we've seen this over the past couple of years with things like pandemics. We've seen this with the trouble in sort of being able to tell false news from good news. Climate change, it applies to corporate decision making. But still, I think, and it's been very motivating to see the emergence of more and more data science courses that are helping students understand the tools to evaluate this data. But being armed, I think, is insufficient if we're going to fall into the trap of being armed and dangerous. And so there's a sense in which it really feels like the tools are one step of the process, and the other whole piece of this is really asking ourselves continuously, how do we avoid fooling ourselves? And so that's the main theme of the course at Berkeley and at the other universities that are teaching it. And I want to give you a little bit of the flavor of some of the concepts in the course. I won't go into all of them in detail. So there's about 26 concepts in the course. And I just want to give you a few because I think the goal from my perspective is really to think about what is a shared vocabulary of scientific thinking concepts that we want to build in our students and in the public, such that we can talk about problems related to data in a way that we can sort of communicate with each other, and in a way that helps us ourselves as individuals and helps us as groups and each other to avoid falling into these thinking traps. So I'm not going to run through this full list, but I just want to give you a few of them. So, for example, shared external reality is one of the founding topics in the course, and really this is starting with that assumption that's saying, if we don't believe there's a reality out there that we can touch, that's independent of our own beliefs and desires and feelings, then there's really nothing to agree on, right? So insofar as data science or science in general is trying to uncover something about the world out there, you have to have that belief in a world out there. There's sense and instrumentation, which is sort of asking why should you believe an instrument? What are the origins of data? Also this sort of idea of, okay, we're teaching statistics, but it's not enough to teach statistics without sort of asking why statistics? Why does this matter? And so signal and noise is a way of sort of motivating that question, because a lot of what we're trying to do, at least in my view of statistics, is find signals in noisy data. Probabilistic thinking is a nice one in the sense of scaffolding our own confidence in the things we say, because as scientists we're not sure, but we're still making claims. So can we get students to be better calibrated? There's a few others. I think, I can go through the list. I think confirmation bias is worth hitting on. There's a whole bunch of things, of course, in the Kahneman and Tversky or thinking fast and slow work, but really in the process of doing data science, and I think anyone who's taught a course with any sort of final project knows, even in our course where we teach our students about confirmation bias, oftentimes the final projects are sort of an exercise in confirmation bias. So how do we get students to think critically about this? How do we get them the tools to avoid falling into confirmation bias? Because I think especially in the data science world, there's a lot of cases in which it's very insidious in the sense that maybe it's not an active confirmation bias. Maybe you're just not looking for bugs when you think you're right, and you're looking for bugs when you think you're wrong, right? And then there's a final piece of the course which I think addresses this question of all of this is great, but how do we work together? I know a lot of us are on Zoom, and so sometimes it might feel like over the past few years that we're sort of living in our own bubbles, but I think there still is a world out there, and we do have to interact with each other. And so how do we sort of separate facts and values? Because both of these things have impacts on the decisions we make as individuals and as a society, as I think is very obvious in our society today. I'm happy to talk about any of these in more detail later on, but I just wanted to give you a quick flavor of the sort of things. And finally, to frame the course and maybe frame some of this discussion in the following manner, which I think is that there's two ways to approach the relationship between scientific thinking and data science. And one is perhaps to integrate into existing data science courses a lot of the course concepts that come up in scientific thinking, and I'm curious to hear about all the other course concepts from the other panelists. And then the second is to sort of say, well, for every concept, or nearly every concept I've mentioned, part of addressing those concepts, I think, can be informed and greatly benefited by teaching data science. And so that's something that we on the Sense and Sensibility and Science team have started thinking about in terms of including some Jupyter notebooks and other data science ways of illustrating these concepts and showing how these concepts come up in the real world, and then maybe offering some smatterings of ways to solve them. And I think this is something that's really important and necessary for the debate and the discussion going forward. So I will leave you there, and I'm happy to talk more about any of this or about the course in the next hour.
Thanks so much, Aditya. Anthony, you're next.
Great, thanks everybody. It's great to be here. Let me share some slides here very quickly and briefly. So as Julia said, I wrote a book called Thinking Clearly with Data that was very much motivated by the same kinds of things that I'm sure you hear from the other panelists, which is that we have so much more data than we've ever had before. So many people say they want to do kind of data-informed decision making and data-informed policy making and so forth. And yet more and more data doesn't do you much good unless you know what to do with it and you know how to think critically about it. One thing we like to say is that thinking and data are complements, not substitutes, which is what you might have thought if you took a traditional data science class and they just told you that we'll just let the data tell us what the right decisions are and so forth. And so there's an opportunity, but there's also a real challenge of this data-driven age, which is why we wrote this book. So part of the goal of the book is to give readers what they would get, what they want to get in a traditional data science course. They'll be exposed to technical tools. They'll learn about regression and hypothesis testing and controlling experiments, et cetera. But the focus, first and foremost, is on thinking rather than on technique. We really want to make sure you're asking the right questions to begin with. You're making the right comparisons. You're thinking critically about what you're doing. And we also want to think about how do you go from quantitative evidence to decisions in a clear and careful way. So that's the pitch for the book. My own background is in political science. I primarily do quantitative analyses of elections and the political process. I wrote this book with Ethan Bueno-Mesquita, who himself is a game theorist, which is very interesting because he is not someone who works primarily with data, but he's a very smart person who's very good at thinking about hard problems. So that was actually very fun for us to work on this together. And for him, who's not a primarily data analyst or data scientist, to think about how do we teach the next generation of critical thinkers so that they'll be better consumers and utilizers of data. Both of us had taught introductory quantitative methods courses and executive education courses for policy people, military people, journalists, et cetera. And we thought a lot about how can we train people to be better consumers of data. As Julia alluded to, we see a lot of students who seem to have mastered the technical material, but don't really know how to think about problems. And when the time comes to actually think through problems themselves, they're ill-equipped. We also see a lot of students who kind of drop out of their data science courses because they just think, oh, this is really technical. This isn't really for me. I'm not really a data kind of mathy person. And they might actually be. It just hasn't been taught in a way that engages them. They haven't been able to see why you might care about these kinds of tools. And so as I was teaching these courses, I couldn't find a book that did what I wanted it to do, and so we decided to write our own book. So some of the things that we at least hope to accomplish in the book, even if we didn't fully achieve those goals. I mean, we tried to write the book in an engaging way, such that instead of just a textbook where you would be assigned in a course and read it because somebody was forcing you to, we tried to make it engaging enough that you might actually just pick up the book and enjoy reading it. You might even curl up in bed at night and read a chapter just for fun. Not to say that lots of people are doing that, but that was at least our goal, to write a textbook that could actually be something you would enjoy reading. And so we tell a lot of stories in the book, and the stories cover a very wide range of substantive areas. We talk about music and sports and medicine and politics and all kinds of different things. And part of that is because you never know exactly, it's only by getting lots of repetition and lots of practice and thinking through some of these problems that some of these skills that we're trying to teach become intuitive. And we're also trying to cover a bunch of different areas because you never know what example is going to appeal to a particular student or a particular reader. We're trying to put the ideas first and the technicality second. Throughout the book, we have kind of our running favorite equation. Is a very simple equation. An estimate is an estimand plus bias plus noise. And you don't want to forget about bias just because right now you're thinking about noise or vice versa. And so we have utilized that as a governing principle for a lot of the lessons in the book. In addition to telling lots of stories, we don't just want to tell lots of stories. We want to have a coherent architecture to the book. We spent a lot of time on that high-level architecture. So our goal is that every chapter tells a story, and that together, in some ways, the book tells a story. And one way of putting the story that the book is telling is that this stuff is, this stuff is not easy. If you want to make good decisions, if you want to do good in our world, it requires clear thinking from everyone, and you can't just leave it to the experts. I think we have lots of examples in our book where you wouldn't want to leave it to the experts. The people who have all the technical training might not actually be really good at the thinking part, and so it is up to all of us to try to do better on that front. So I'm just going to give you a very brief overview of the kinds of things you would see in the book and also in the courses that I teach. Part one of the book is primarily just about establishing a common language. Why are we here? What are we doing? And what do we even mean by some of these big terms? Like correlation and causation, which is what does a correlation even mean? What do we even mean by causation? Most data science courses would not have a chapter on the philosophy of causation, but I think it's actually extremely important to think through that. If you're going to be answering causal questions, you should spend a lot of time thinking about what you're actually doing and what do you mean, and what are you not doing, of course. Part two of the book is about figuring out whether a relationship exists or not. So this is where students will learn about regression, they'll learn about statistical inference. Some of these things are things you would learn in a traditional course, statistics course or data science course. We also spend a lot of time talking about p-hacking and p-screening and the replication crisis and so forth, which is not something you'd get in a traditional course. And we also talk about reversion to the mean, which is highly related to these concepts and seems to be something that almost nobody really understands on a deep level, but we think is really important in order to actually do this kind of work to figure out, do I have a bunch of false positives or overestimates, et cetera. Part three of the course is about causal relationships. So suppose we know we've got a real relationship. How do I know if it tells us anything about some causal relationship of interest? And so here we introduce experiments, regression discontinuity designs, diff and diff designs, the kind of things you would get in a more advanced econometrics class focused on causal inference, the kinds of things you would get in mostly harmless econometrics or mastering metrics. And we also spend some time talking about causal mechanisms and talking about what we can and can't say in the realm of causal mechanisms. And then part four of the book is the kind of thing that you really wouldn't get in a traditional course. That's where we talk about how do you go from quantitative evidence to actually making better decisions. And so that's going to include things like how do you generate statistics that are most useful for you in decision making. Some statistics are much more useful than others. And that would include things like Bayes' rule. How do you translate a piece of quantitative evidence to update your beliefs? But it includes lots of things like that. Measure Your Mission focuses on similar problems where you want to make sure your quantitative measures actually match your goals. And it's pretty easy to slip into a mistake where you just measure the thing that's easy to measure without thinking about whether that actually matches your goals or not. And of course, in that same chapter, we talk about strategic adaptation from a game theory perspective. We talk about things like selection bias. We talk about all of the ways in which people can often fail to measure their mission. And then the last chapter of the book focuses on the limits of quantification, of which there are many, and I think a good data scientist should be aware of those. And one of those limits is that data alone never tells you what the right decision is. The right decision is some combination of your prior beliefs plus your values plus the evidence. And so we spend a lot of time talking about that, including things like what do you do when the evidence isn't clear, and how do you convey uncertainty in that way, and how do you how do you think ethically about the use of data and so forth. So so we hope that kind of stuff is useful for readers and for students, and we think should be kind of part of the required canon of a data science curriculum, even if not all of that is. So I'm looking forward to our discussion. Thanks so much for your time.
Thanks, Anthony. Niki.
Cool. Someone wrote in the chat if you could drop in the title of the book and the two authors on there.
Yeah.
All right, so hello everyone. I'm Niki Cotton. I'm a math teacher here in Chicago. I'm going into my 9th year teaching, something like that. And so I work with Skew the Script, like in our free time that we never get. And the cool thing about Skew the Script is, one, I did not make it. Dash did, and he's a really cool guy, and I really wanted to share him. If I could, and once he's finished that, if I can get the ability to share, that'd be great. But Dash did what almost every second year new teacher does, and he wanted to get rid of everything. And so he taught the first year teaching AP Stats, did not like it, found that the students were very bored, and he wanted to know what they wanted to learn about. And so instead of teaching the reading the book and then at the end having application problems, we have application problems. and then we figure out which tools to use. And so since it's high school, we don't really just give them all the tools. We show them, here is central tendency. Let's talk about this. We already know what the problem is. How can we relate? How can we use that tool to solve that problem? And so when it comes to content, let me see. Yeah, I still can't.
You can share if you want to.
Yeah, well, it says to say, I don't think I'm a host, but while you're fixing that, and so for me, I joined the team 2 years ago with the same problem. I had just started the pandemic school year, and I had the dreaded PowerPoint slides to teach AP stats, and students were dropping like flies. And so what I did was I went on Google and I was like, I gotta find something. Like, I am bored. If I'm bored, the students are bored. This is terrible. And so I found his curriculum. And so this is what it looks like. It's really, really cool. So first, this is Dash. I want to give him 100% full cred. He's down there in Texas. And like I said, he wanted the students to be happy and he wanted them to be engaged. And so he just asked them, what do you want to learn about? The beauty of this is that it worked for him, but I don't want every teacher to think that you can just do the same thing. If you ask your students, hey, what do you want to learn about? And you're going to get an array of like policing and race, food deserts. Most of the time, they won't say anything at all. And so what I ended up doing at the beginning of the second quarter that I found Ski the Script, I turned on the news. And so for the first 10 minutes, we watched the news in every class, and we would take something out of the news, find the math to fix whatever was going on in the news. And so that worked out very well. And I loved every minute of it. And so once I hooked into that, I just kept going. And so some of the highlights from his curriculum when it comes to what to focus on, we have social issues. And the big thing about the social issues, it's something that I have to push a lot whenever we have these trainings or whenever we have these discussions about Skew the Script. We're not a bipartisan, we're not a left, right, we're nonpartisan. All we do is state facts, and students make decisions based on those facts. And so they get to investigate what they see, what they hear, and make those decisions, the same thing that the other panelists are talking about. Like, we're doing the same thing at the high school level, just to get them ready for when they go to y'all, they know what they're doing. And so science and medicine, and we do some fun things where we finally end the argument about LeBron versus Michael Jordan. And we prove mathematically that one of them is the greatest, and it's Michael Jordan, but onward. And so this is how it's grouped together. And it goes through all of the requirements for AP stats. And so there's also an added part down here for the projects, which is really cool. And this is either during the unit or at the end after the AP test. Because the hard thing about teaching a tested course, and I'm sure everybody knows this, is that when you have either an EO or end of course test or an AP exam you have to prepare for, or the SAT or ACT, teachers are crunched for time. And so we're just honed in on hitting those skills, but we really want the students to experience this holistically, right? So after we go through all of these skills at the end of the year, now we can do a really cool like machine learning project, or we can focus on COVID. We hit COVID really hard for those 2 years. And so that's the gist of Skew the Script. For me in my role, I'm the curriculum writer. And so I go in and I'm editing things that are going on with AP stats. I'm also writing the curriculum for AP Pre-Cal, because that's a new, College Board is pushing out Pre-Cal. And so we're going to be the first one to have that curriculum. And that's the big thing, is we're making it relevant. You know, math is the most important subject on the planet, and it's everywhere, you know. And I remember when I was in high school, they would say math is everywhere, but I didn't see it. And so now I'm watching the news and I'm like reading books and I'm listening to podcasts. I actually have the capacity to discern what I believe to be true and what's not true. And so I look forward to engaging with y'all as well. And yeah, let's have some fun.
Thanks a lot, Niki, and sorry for the sharing glitch.
It's okay.
Daniel, okay. Daniel, you're next.
Okay, hi everyone. So I teach a course about statistical inferences, and I would say that teaches basically pretty basic principles in statistics, starting from things like p-values and effect sizes and confidence intervals. And there's a lot of material about this, but the main reason to create a course myself on this topic is indeed, as mentioned in the beginning, the replication crisis. But maybe more specifically, actually, that after this replication crisis, I was a postdoc, I think, at this time, and I realized that I was just basically incompetent in terms of doing good research. So it turns out that a lot of findings in science were not reliable. And there were all these things that were relevant to doing a good study, but nobody really had taught us about these things. And moreover, nobody has really taught us that some of the things we were doing were actually actively harmful. And we thought, yeah, it can't be that bad. And we couldn't really understand why it would be bad. And nobody was able to explain why it was bad in a good way. So, and then there's a final thing, and that is that sometimes in these discussions we would say, yeah, so what are we supposed to do then? And there was also not a lot, right? So in terms of things, not working out, sometimes that was mentioned, but then how do we do this in practice? So all these things together sort of are the core of the course that I teach. So I try to point out to people why certain practices are problematic, but also if they would design a study tomorrow or run a study tomorrow, whether this is for their bachelor thesis or their master thesis or because they're a PhD student, what are they supposed to do tomorrow, basically? And what is the stuff that really matters? And one of the themes is also not fooling yourself. There's a large disconnect between how we teach science and what we actually do in practice, which led to this replication crisis, and people were massively fooling themselves. So I try to, in a sort of optimistic way, showing that we can do better, and we can all learn how to do better, of course, right? That's part of being a scientist as well. Explain how we should improve these things. One of the cores of this is because my audience, I would say, at least my background is in psychology, and psychologists don't go into science because they like numbers. They go into science because they like people. So there's a rule in our field that every formula that you would present, you lose half your audience, basically. So what I try to do instead is teach through simulation. And the main reason is that I found this a very intuitive way to finally understand these things. So we don't do thousands of studies in our life, so we don't really see the consequences of certain things we do, but you can simulate the consequences of these things. So if you start with simulation, then things become more visible to people, I think, than if you just use formulas. And sometimes I do add them somewhere, but maybe after the basic concept has been explained. So that is one thing. And another aspect is that I tried to do this in classrooms for a while, but it turned out to be very difficult because people need such different times to understand these things, or different amount of time to play around with certain things. So first I tried to just explain, and I do think that you really need the connection, because the things you talk about, they don't become concrete unless you then hands-on do something really with it. So I tried to do this in person first, where I would say something, let them play around. Then it became sort of a chaos because some people were halfway through, and then I had to go on to the next thing. And then I tried to talk and then send them home and let them do stuff, and they wouldn't do it, so it also didn't work. And then I thought, okay, I'll make like an online course where there are short videos. They can watch them in double speed if they, nowadays they do this, and then practice and do it in their own sort of speed. And that worked surprisingly well. Turned out to be kind of advantageous during the pandemic to have made this. And another benefit of this is that I think this material is relative, I wouldn't say new, because a lot of people have complaining about a lot of these things for like half a century. But putting them in practice and really doing something about them is new. So stop doing these bad things and start doing these things right. That is relatively new. And what you see is that there are a lot of places where people don't have access to teaching materials related to these topics, whereas they're quite important. So one thing I liked about having these videos is that you can go online to a platform like Coursera, and there most of the students that enroll are actually people that would never otherwise be in these classes, right? A lot of people from India or South America, for example. And there especially, they really appreciate having access to these materials. And that's, I sort of thought like, if it turns out not dramatically bad, then I might put it online. But I think that's another benefit of this. So the combination of experiencing this and then also focusing on things that really matter in practice. So I think it's mentioned before, you have to make it relevant, like Niki mentioned this as well. But for researchers, what is relevant is, okay, so what do I do with these numbers that I'm computing? How do I really interpret them? So very often we stop at the moment a number is computed, and people don't really know what to do with these numbers, surprisingly. And So the audience is mainly these bachelor students or master students, but on the Coursera page, I first mentioned this originally, like this is for third year bachelor, maybe master, maybe a good refresher for a beginning PhD student. But then a professor emailed me and said, yeah, I found this course super useful because most of this stuff was never taught to me as well. Can you please erase that text? Because if I send it to other full professors, because I think they benefit from it, they might feel insulted that it is for bachelor students. And I think the thing here, surprisingly, is then that these are basic things that apparently nobody was taught, right? So that just exists. And I think it's also in Anthony's book, many of these things like p-hacking, nobody was just talking about this. So yeah, making that stuff available is sort of the core. So yeah, that's what I try to do. Thanks.
Great, thank you so much. So we'll move to the going through the questions that we had looked at earlier. And we'll use the same order, but to not make this too stiff, if people have comments across, just feel free to do that as well. So the first question is, what are you hoping that students will understand after your course that they didn't know before, especially in terms of habits that go beyond just the technical skills? Okay, Aditya.
Yeah, I think, well, first of all, thank you all. I find this fascinating and want to talk more about your courses. But to get to your question, Julia, I think our course, first of all, I should say, we try to recruit students from across the 4 years, so sort of first years through fourth years, and across different disciplines. So we try pretty hard to get about 1/3 humanities, 1/3 social sciences, and 1/3 natural sciences. And what that means is that the technical capabilities of the students coming into the course vary very much. There's some students, we have a few exercises in Jupyter notebooks and such, and some students find that really easy. But I think what we want all of the students to sort of come out with, and there's some slightly different goals depending on their starting point, of course, is a few things. I think, first of all, the sense that these scientific thinking concepts, I mean, all of the ones we've been talking about now, are things that you want to carry with you pretty much all the time, right? So first, there's a sense in which these concepts are relevant. Like Niki, you were saying, I mean, they're relevant. We've had students use this. We have a final project in the course, and they've gone anywhere from how do we solve global pollution to should I break up with my partner? And this is a real project, right? So there's a sense in which we want students to realize that there are ways to break down problems, no matter how trivial it may seem. And of course, I think the second part of it is to present a cautiously optimistic view of our ability to discover things in the world. And we always joke and say what we want is for every person who takes our course to then go and run for office, and we want everyone in Congress and in the Senate and everyone to have taken this sort of course, because it really feels like that is the end goal here, is to have a group of people, a group of students with a shared vocabulary who can sort of say, okay, we've tried a problem and it didn't work, and let's work together with these tools and with these sort of cautionary tales to come up with a better solution. And so I think that's really what we hope students take out of it, is a mindset, in addition to some clear technical skills as well. But I think the mindset is the big one.
Cool. Anthony.
Sure. Yeah, for my courses and for my book, I mean, of course I have, lots of ambitious goals. Realistically, I'd really like students to not select on the dependent variable and to learn and to recognize when other people are selecting the dependent variable. And even that, I think, is more difficult than you would think. But, so I mean, yes, I want in general, of course, I would love it if some students are inspired to go on to a career doing data analysis. That's fantastic, and to be better at it. I would, but I really want students to at least retain a few critical thinking skills, like selecting the dependent variable, which I kind of mentioned as a joke, although I actually think it's a very important one. Like, you'll see it every day if you learn to look for it, and you'll fall for it all the time if you haven't practiced that thinking skill. And there are a few others like that, just learning to look for what's likely a false positive, to think about things like confounders and so forth, and to think about and to be able to combine their normative values with evidence in a reasonable way. I mean, those are basic thinking skills that I would like to, I want every educated person to have. I'd like all the judges and elected officials and so forth to have. I'm not, I don't think my book alone is going to achieve that, but I hope that, by working at this from lots of different angles, we can improve the extent to which people have those skills.
Great, Niki.
Yeah, I think we're all on the same page here, except I'm a little bit lower. I hope that when mine get to you, that they're able to compute and do things in a big fashion, but they're definitely doing the same thing about figuring things out. I mean, that's pretty much the goal, right? Like I lean a lot on Jordan Ellenberg. Like I want them to not be wrong. Like I'm tired of having conversations with students and then eventually with parents where they're just leaning on some just false way of coming up with the conclusion, right? Like it's just, I love at the end of the year, even this past year, where students are now, even though it's something super small, super small, but I no longer hear like, yeah, about 70% of people. And it's like, how'd you know 7? Like that, getting out of that space where they're just making random like inferences. That's like the big goal for a Scuba Script, is just to make it not only accessible to everybody, because it already is, but just making it so every single person can take away at minimum one thing. And it's just gonna change their life, where it's just anything as small as how you talk to somebody, even with the breaking up, like weighing your pros and cons and figuring out like who you're getting information from, like, are you actually doing a good sampling method? We're doing things like that. Or something big, right? Like one of my seniors just graduated and he wants to go and be an alderman now. And it's like, why do you want to do that? Like just that, the idea of wanting to change because you know how to be right. Like you finally figured out how to be right.
Niki, I think I missed the 70% thing. Is that your students are just making up statistics?
Making it up. Just make it up. Just, and I every time they would say that, I'll be like, who'd you ask? Who'd you?
There's some national role models that they might be mimicking.
Oh, 100%. 100%. It's just like, even like in Chicago, that's a big thing. I started my class because I'm very all over the place. And so the first unit I make up is about conspiracy theories. And I have them just list them. Like, what's something you believe that others don't think is true? And if you ever need joy in your life, find a teenager and ask them about a conspiracy theory, and you will be happy for at least three years. They're amazing. And just hearing where they get their information, and then they have to go and prove it, and it's wild. And so math, man, math.
Yeah. Cool. Daniel?
Yeah, I think this is very funny because at the level at which I teach, you have exactly the same problem and the same lack of understanding of things. So it can, this question, like if somebody says 70% and then you ask why, like where did this come from? But what I notice up to the level of practicing scientists, which I also teach sometimes in workshops, for example, you can just very often ask them the question, why? Like, why is this a thing? Like, it doesn't matter. Like the interpretation of a number, or, like in statistics, for example, people often design statistical tests and they have to put alpha levels somewhere and they have to aim for statistical power. And then in our courses, we teach them certain things. We say things like, oh, the alpha level is like 5% and power is sort of 80%, and that's good. But then you just ask, why? And then they don't know the answer to these things. So there are very basic things that are central to how they design their studies, and they can't answer a single why question. And the goal basically of my course, I explicitly say this, is that at least if I ask you why about everything, you should give one answer. I mean, there's also always layers below layers and layers. You don't have to go all the way down, but for certain basic, really important central things when you do research, you should be able to know, why. Why is this a thing? So it's sort of combating mindless use of statistics, I hope, giving people really the tools to have a little bit more of a foundation of what's underneath this. Why am I doing this thing rather mindlessly, right? But really replacing it, no, I'm doing this thing because of some reason that I can actually articulate and understand. So that is sort of my goal. And I guess maybe for other courses, like it sounds like if you present a mean, that's the same thing. Like, why am I giving this number? Because of some reason that I can understand. I can articulate why this is a thing, just on one level, you know? I mean, and that is hopefully the goal, I would say. Yeah.
Great. So the next question is about where your approach or your course falls on the spectrum of using a lot of examples. You might be familiar with the 9 Pitfalls of Data Science book and others, versus having a heavy emphasis on frameworks, like Anthony was mentioning, that tie all these examples together. And so how are you balancing or prioritizing those, and what kind of frameworks are you using that tie everything together? Aditya.
Yeah, I think that's a great question. So in our course, what we've done is tried as much as possible to sort of tell a big picture story about why this is important. It's certainly been it's not the easiest thing in the world, but the framing that we use a lot is something like saying, look, there's these philosophical underpinnings, and that's really how we like to start the course. So things like this shared reality concept, right? Or there's a few, we really don't like, I don't love the idea of isms, but there's a few sort of isms that you need to introduce to students so they have a sense of the broader picture, and this basic idea of what is a mathematical model, right? I mean, in the sense that we're trying to get a sense of the reality out there. So that's the first piece. The second piece is sort of structured as a whole list of scientific tools, really. So things like signal and noise and instrumentation and all of these things. So what are the things you might learn as a graduate student in physics or some other natural science? Then, of course, there's the piece of thinking traps, the psychological biases and such. And then finally, group decision making. So we try to sort of tell a story of saying the first part of the course is learning why, then learning about the ways in which we fool ourselves, how to solve those as individuals, and then in the final piece we try to bring in a lot of experts and guests and have the students sort of ask questions to some faculty member from somewhere, and really try to engage in some of the group decision-making activities like deliberative polling. So we usually put on a deliberative poll for the students and things like that. As far as examples, I think the course is littered with examples, and it's an open question about whether it would be better if there were sort of 2 or 3 big examples that we take throughout. We got a taste for that, honestly, with COVID, because it comes up every week, and every course concept is relevant to that. And the feedback we got from students was surprisingly positive. I mean, on the teaching staff, I remember every week we would sort of sit there thinking, is this too depressing that we're going to do another week on COVID? And of course, it is awful. But at the same time, we got the feedback from students that it helped them deal with the stress and the uncertainty, because they sort of had some set of frameworks every week of thinking somewhat systematically about this. So I do think we're short on examples, but I think there is that possibility, and it seems like it might be promising.
And one of the things I love about SNSNS is that there's a lot of experiential learning and games and things to really be part of an experience of the difference between signal and noise or randomness, or how the instruments work and so on, that make it fun. Anthony.
Yeah. For us, we did spend a lot of time on the high level architecture of our book and our courses, including just what's the right order to present everything in, and how does everything relate to everything else. And so I do spend a lot of time when I'm teaching this materials on where have we been and where are we going and why are we where we are right now. I think all of that stuff is very relevant. Otherwise, it's it'd be easy for classes like this to fall into like, oh, here's another example of someone doing something stupid, and I remember that example and maybe that was fun, but I'm not really able to think about, like, if I see a new example, I won't be able to say like what's wrong with it or what's right about it. And so we spend a lot of time trying to do that in courses. And I also try, as something comes up, to just not forget the previous lessons, but to kind of build upon previous lessons and combine them. So for example, students might say, they might look at something and say, oh, that's a spurious correlation. And you might say, okay, like, let's think for a second, why do you think that's a spurious correlation? Are you are you making an argument based on chapter 7 of our book or chapter 8 or chapter 9, you know, and we actually spend some, and very often actually they haven't quite figured it out yet. And very often that's actually very useful for them to actually, in this case, that's probably not even a real correlation. If you collected some new data, it probably wouldn't even be there, which is very different than saying, no, I believe it's a real correlation. I just don't think it means what the person presenting it thinks it means. And so those are opportunities for us to kind of not just forget the lessons from previous chapters and previous course, you know, previous lectures, but to integrate what we know. So I think it's very hard, and I think it requires a lot of active effort, and I'm not convinced that we have exactly the right way of doing it, but I think that high level architecture is really important for a course in a book like this.
Yeah. Niki.
Yeah, so we abide by College Board. And so when it comes to our framework, I'm heavily aligned to that. And we also use most of the popular books, the popular textbooks, and we just go through and on the website, it'll show you where each lesson, each skill can be found in that textbook in case you do need additional practice. Because that is one thing that Skew the Script doesn't give. We don't give the worksheet of like, here's 30 problems, go home and do them. That you can find in an open resource textbook. And so for us, it's the things you can't Google, right? Like that's what we focus on teaching in our curriculum, is stuff you can't Google. And that's the part I love the most.
Mm-hmm. Yeah. Cool. Daniel?
Yeah, there are some questions in the chat that I'm tempted to already start about with the difference between frequentist debate and statistics, but I'll wait for a second. So I have a list of topics in the course that I need to go through. So there's not really an overarching theme, but what I try to do is give examples, and then very specifically examples of people messing up in ways that are quite consequential, or maybe very well known, for example. And the goal there is to point out things that most people in their environment probably believe, but then to explain to them why it's wrong. So that hopefully, and sometimes I joke, like if you've learned this thing, you're now like smarter than 95% of the people who talk about this. And one example actually, so we just heard talk about confirmation bias by Daniel Kahneman and Tversky. But in this book, Thinking Fast and Slow, there are a couple of studies where Kahneman interprets the literature in a very flawed way. So he trusts studies which are very flawed. And I explained to students that, specific examples relating to certain topics. So there's one about effect sizes, for example, where in a book he talks about hungry judges. And these judges, the hungrier they become over time, the more severe they punish because they are depleted. And it's just not true. I mean, that's just a misinterpretation of the effect. I emailed with Daniel Kahneman about it, tried to explain it. So I tell sort of the background story of that as well. And then by every unit having one example where students go home and like, oh, wow, I now know this thing. And most people don't know this. And even Nobel Prize winners make this mistake. Wow. That's sort of my hope, that they feel, like motivated and that they really learned something new, basically.
Great. I want to get to one question that was Niki's question before we turn it over to the audience. And so the question is, in how far your curriculum does this differently to make data science more accessible and relevant to a broader audience? Like students who come in thinking they hate math, like Anthony mentioned, like Black and Brown students, LGBTQ youth, and others, and who are your target students who aren't targeted in the typical data science classes? Anthony? Oh, no, sorry, Aditya. I got it mixed up.
Yeah, I think, I mean, that feels like it's such an important thing to address. And part of it, I think I already mentioned, in the sense that we first of all really try hard to get a diverse student population, and I think that's important. And I think that's especially important in this sort of field for a couple reasons, largely because, and I think it depends on the university, but a lot of universities, if you look at the CS population, or you look at the data science, the students who are in that major, it's a pretty homogenized population. And I don't think that just interacting with that group is preparing our students to make decisions out in the real world, where data meets facts and values and group decision-making strategies and a whole bunch of these other things. So one of the things we do is try to have an application for students, in such that we can sort of screen students before they get into the course. as well as try to, so we've been including more and more sort of technical modules in the course over the past few years, but trying to make the idea of a Jupyter notebook less scary. So a lot of what we do in the first 4 or 5 weeks is give students Jupyter notebooks in which their physical action is just shift enter, but as Anthony was saying earlier, the entire point is not to fiddle with the notebook, but to think about the results. So it's a lot of sort of move these sliders around, play with this thing, such that we're not actually teaching any of the data science techniques or teaching them how to code. But the hope is that by taking a course like this, students who I think would come into our course who are not scared, once they played with a few notebooks, might then be empowered to go and take a course like Data 8 or something like this, which I think initially they might be too terrified to take. And our whole goal there is to say that, look, yes, maybe the coding is tricky. Maybe you don't know what Python is and think it's only a snake. But if you understand that the thinking process is the same, whether you think about it in terms of variables and machine learning code, or whether you think about it in terms of words and sort of concepts, then I think that makes that translation a little bit easier.
Anthony.
Yeah, I in part answered some of this question earlier when I talked about all the effort we've tried to make this kind of book and course accessible to a wide range of students with a wide range of backgrounds, including telling lots of different stories and having lots of examples and so forth, and trying to focus on the thinking rather than the technique. One of the things that I always tell my students is this is not a programming course. This is a thinking course. And I do have programming kinds of activities in the class where they're analyzing data. And I'll tell them, if you ever have problem with the programming, even in my, I'll have a class with 150 students. If I say, if you know what you want to do with the data and you can't figure out how to make Stata or R or whatever you're using, do that for you, email me and I will write the code for you. And very often students learn from that process that it really was a thinking issue and not a coding issue. And actually think that turns out to be a very useful exercise for the students, because sometimes they'll get discouraged and like, oh, I don't like Stata or something. And then it turns out actually it wasn't Stata wasn't the problem. They just hadn't thought enough about what they wanted to do. And so I tried as much as I can to remove that part of it to help them with the thinking. And it is extremely rewarding when I get emails from students at the end of a class saying, I never thought of myself as a mathy stats kind of person. This was the one quantitative methods class I was required to take for my major, but it turns out I actually really love it and I actually want to do more of it. And that's fantastic. And that's really rewarding. And so that's partly why, we tried to do this to begin with. The one part of the question that I want to push back on is this notion that, this is different, different people can disagree on this, but I want to somewhat reject the notion that we have to, the way to teach data science is different for Black and brown students or for LGBTQ+ students, et cetera. I think lots of people have different backgrounds and lots of people struggle with different things, but on some level, I want to say this is the way to teach data science for everyone. And in some ways, I don't need to fixate on various aspects of your identity. I want to teach a class that's accessible to a wide range of people. And of course, I want my courses to be inclusive and welcoming to everybody. And there are lots of things we can do to do that. But in some ways, I don't think that, fixating on identity is a productive thing in a lot of cases. So I'm happy to hear from others on that as well.
Niki.
Yeah, so for me, it's the big reason why I do bring it up is because there is a lack of knowing what the struggle is like when you enter those spaces. And so I know a lot of, and again, a big reason why I want to bring it up to the same thing that Anthony said, like, it's not a matter of like, you shouldn't have separate, curriculum. Like we're going to put some songs in it and we're going to make it where you love it and you can dance, and it's that cheapens it, right? Like you definitely want to keep the exact same material. I think to make it accessible to Black and brown and to any marginalized community, because as we're seeing now, like that community seems to be getting bigger and bigger. It's just giving the students the room for respect, where they find these tools and you're working with them, you're making sure they can understand them so that when they get into a space, they're confident to speak and they're receiving that respect because what they're saying is factual and it's not just from a feeling, or they don't feel like they should say anything at all because people are speaking and they're using all these scientific words and this very hard language that just really hard to like dive into. And that makes them, at least for me, with my experience in these 9 years of teaching, it makes us feel small. We feel very, very small in these rooms. And so we don't want to say anything. And so the big push when it comes to Skew the Script is we make it relatable so that you can see, you can use it anywhere. Anybody can use it. Like it's the beauty of the mathematics and data science is that everybody can use it all the time. And it actually goes to one of the questions, I think it was Julian that put in, for the topics that are underserved. Since students spend all their time on, I'm not even gonna exaggerate, all of their time, every second on social media of some variant, that's still data, right? Like they should still be able to look at that and make decisions the exact same way. And that's the part that ensures it serves all communities, is just one, giving the confidence, for teaching the confidence, 2, allowing them to have the floor for respect, but also letting them be wrong. That's something that a lot of students are afraid of. They don't want to be wrong, but they also, so instead of being wrong, they won't say anything at all. And so just showing them that mistakes are okay, and people have made mistakes since the beginning of time. Just showing them that you can make those mistakes. We can show it's a mistake mathematically. We can show how to fix it. We can show all these things. And we might also get to a problem where we don't have a solution. And so just, again, giving them that confidence and respect has changed the game for a lot of students.
Thanks, Niki. Daniel.
Yeah, so one thing is kind of simple in it, but I just want to briefly mention it, is that trying to design a course with minimal prerequisites. So for example, in the course I use R, but I really use it as a calculator and I say so, and I really write instructions in the assignments like go to line 9 and replace the number 10 with number 20, so that basically anybody could follow through. That's a simple thing. My main focus is mainly on getting this content to people in countries where they otherwise would not have access to education, especially not education like this. For example, countries like India, for example. And when I designed the course, I tried to early on, for example, provide many metaphors that are not just linked to Western culture. Like in the first lecture, for example, I cite from the Bhagavad Gita, which is a Hinduist text, and Zen koans from Japan. It's nice because some students really appreciate it, right? They rarely see references to those kind of texts in their student material, for example, but of course they see them in their own culture all the time. So I think that's nice. And another thing that I've tried but not really done is trying to translate material, because I think a lot of people don't speak English, of course, and especially people we would like to have careers in, for example, data science, because it's a great job you can do from anywhere in the world. So it would be great to translate material to more languages. I don't really know how. So I know on Coursera, they actually provide you with a center where people can volunteer and translate, for example, the subtitles to all your videos, which has happened in Chinese, which is important in science, especially because China has a sort of problem with science and not with science, but let's say these kind of problematic practices are quite common there, but nobody talks about it. So anyway, so there was a group of Chinese researchers who really wanted to translate it, and they've done this. On the other hand, I, for example, failed to translate it into Spanish, which I've tried a couple of times, but the volunteer initiative didn't work out. And then I'm not really sure how to, for example, get money to do this, but I really think it would expand the reach quite substantially. So it's something that I would love to do, but I'm not really sure how. So I managed in some ways, but there are also some ways which I failed so far to make it available broader, but yeah.
Okay, so let's open it up for the Q&A questions from you in the audience. There's a couple. Let me start with the one in the chat here that Daniel, you were itching to answer, and we can now open up the order. Whoever feels like answering, feel free. If you don't have an answer, feel free to skip it. So this is a question from Julian, asking, one reason why statistics are often found off-putting is that the frequentist way of thinking is profoundly counterintuitive to most people. How have innovations in data science helped overcome this barrier in your experience? And it is easy to interpret Bayesian methods now for a lot of problems, but how do you find they are digested by students? And then I believe this is the second part of the question. Well, maybe let's focus on this one first because the other part is from the same person, but a separate question. Daniel, do you want to get started on that one?
Yeah, well, the reason I like this question is because I'm maybe one of the 3 people left in the world who actually like p-values and find them useful in the experiments that I do. But also what I try to do is always go against, maybe it's a bit of my nature, but I always try to go against the prevalent sort of norms and tendencies. So it's definitely true that Bayesian statistics is becoming increasingly popular. I do add it to my course because I think not enough people are exposed to it. So I teach it in a very balanced way. But I also maybe to make it fun for myself is actually go against this kind of thing a little bit and make people question, for example, whether in science statistical inferences should be influenced by prior beliefs, or whether they should be only based on the data. So I like that philosophical discussion. And then I try to fight a little bit actually for the p-values, defending them, because I try to make it sort of like the avocado toast of statistics again, make them hip again. That's my goal for myself, which sometimes works and, sometimes not. But at least
No.
presenting them side by side. No. Yeah, I am. It's a lost fight, maybe, but
That would be like,
but it's a nice challenge, though. No, really, I think it's a nice challenge to go against this a little bit and try to defend these poor little p-values and present it like this to students. So yeah.
P-values are the asparagus and corn
yeah.
statistics.
For everyone who didn't join before, we were having this debate about pizza that has corn and asparagus on it, and Niki was not a fan. Anyone else who has opinions about this?
I'll say one thing. I like Daniel. I like p-values. They're very useful, and there's a reason that we have them. One of the most important things I think students can get out of my course is to learn what a p-value is not. I think that's the few things that I know they do remember because I harp on it so much. And so I do think, for a lot of things, I'm not sure how successful I am, but I think I annoy them enough when that one, where they actually learn what a p-value is and isn't, which is very useful. Usually that's in chapter 6 of our book. And I will tease them and say, I know that's not really what you want to know. What you really want to know is is this true? You just read the study that said that judges punish more when they're hungry or something like that. And now you want to know, is this actually true? And we're going to talk about that in chapter 15. And they're very antsy. The weight is actually very difficult for them because they really want to answer, which is fantastic. And when we get there, I don't do technical Bayesian statistics, but one thing we do Bayes rule and we apply it to the traditional, scientific study in frequent statistics kind of problem. You also need to know what your prior is, and you also need to know the power of the study. And those are the scientists almost never think about. Power is something we should talk a lot more about in these classes and as scientists as well. How many times have you ever seen a presentation where someone's presented a significant result and said, hey, what was the power of your study? And they would say, who cares? I got a significant result. It turns out you should actually care a lot, because if it was a low-powered study, then conditional on getting a significant result, it's much more likely to be a false positive. And I actually wrote something about this in the Political Methodologist, which was somewhat controversial because it's something people just don't understand enough. So I think that level of thinking is extremely important. And I think teaching students his role and teaching students how to go from frequent statistics to the things they actually care about is incredibly important and isn't done enough, even if you don't teach them how to do some fancy Bayesian statistics thing on the computer.
Yeah, I think the PowerPoint is very well taken, and one of the things we sort of harp on, and I think in the physics world, it's sort of approached from the look elsewhere effect perspective, right? Of how often do people divide by the number of variables that they actually are looking at? I think it's very rare. It feels like the other portion of this that is not necessarily Bayesian in sort of proper terms, but is getting close, that I think has some value, is this notion of sort of calibrating your probability. So one of the pieces of our course is sort of saying, well, most people are quite overconfident. So if I say I'm 90% sure about something, it's probably only 60% likely to happen, right? And so there's this sense of, sure, you can have priors, but how good are your estimates of probabilities when you don't have other information? And so in the past, we designed one of these stupid little apps to get people to make estimates, and then sort of tell them how they're right, and then you can sort of track whether they're going to correlate over time. After about 5,000 such iterations, we were like, oh, this is not getting anywhere. So now we sort of just tell them a little bit about super forecasters and sort of weather forecasting and the ways in which you want to set up a system if you're going to make these probabilistic estimates such that you get feedback, and then you can start to make better estimates. Because I think a lot of research shows that if you get timely feedback and you get feedback in a systematic manner, you can get better at your own estimates.
Anything else on this? Okay.
Well, maybe one tiny thing. So there's this thing called Lindsley's paradox, where the two approaches, the frequentist approach and the Bayesian approach, actually conflict and lead to different conclusions. And that's definitely one of the things that if you explain it to people, it's sort of like really an eye-opener, because it means that a statistically significant p-value can actually be support for the null hypothesis. And that's just sort of, it blows their mind when they figure out that these two different perspectives can conflict like this way. And in my view, that's a very nice introduction to getting these frequentists to think about at least Bayesian statistics. Yeah.
Okay, let's switch to a question by Matthew Brett, and he's asking, can I ask the panel to name their favorite big data interpretation, or I guess big data error, and how can we use that error as a teaching point?
If nobody else wants to start, then I'm happy to do so. So one of my favorite examples that I use in teaching is a study by Facebook about emotional contagion that was quite controversial a couple of years ago, because Facebook had manipulated people's user feed, and by manipulating them, removing some positive posts by friends or removing some negative posts by friends, they looked at whether people typed in more positive or negative status updates. And basically they said, yeah, we're able to manipulate people's mood in this effect. And which statistically is true, but it's a great lesson of having big data. Like they had 64 million status updates, which is a lot. And the effect they observed is sort of in the same effect size as how much my hair has grown since we're here. Like, it's just not noticeable. Like, it's so super tiny. It's not noticeable on an individual level. It has no practical consequences for anything. But there was a huge ruckus. So in my material, I have a person who writes, yeah, you know, and mood is correlated with suicide. So Facebook basically made people maybe commit suicide. It's so unethical, but it's really an effect that you would not notice. And then we compute how many words they would have to type to have one more positive word. And it's in the like 16,000s. And I ask, how often do you write a status update like this? They say never. So it's a good lesson that having a lot of data doesn't mean you have practical effects. Yeah.
Yeah, I mean, I have lots of them. I don't know if I could pick one favorite one. In some ways, most of the things I talk about in my courses are not big data mistakes; they're thinking mistakes that could apply to any kind of data analysis, not just big data. But big data does kind of exacerbate some of these problems, as Daniel suggested. Big data can make it easy to forget about substantive significance and fixate too much on statistical significance. Big data can exacerbate the problem of multiple testing and selective reporting. And so big data doesn't make all of these things worse. I've taught about the Google flu trends example, which maybe some of you are aware of, where they heroically tried to predict where were there likely to be outbreaks of flu based on people's Google search history. And it turns out that the mistake was incredibly simple. Like, it wasn't, you might have thought of all of the very complicated technical mistakes they could have made, but essentially they just didn't recalibrate the model every year. And so like, if people's searching behavior changed a little bit over time, like the model would work well for a little while and then eventually would just go way off course. And so it seems like an incredibly basic kind of thing. And so one reason I like that example is not because it's because these guys are brilliant, right? Like these are incredibly brilliant engineers at Google who have PhDs in computer science and statistics and so forth, and they've been trained in all these technical things. And the mistake that turned out to have kind of ruined them was this really basic one. And then they actually just closed down the Google Flu Trends tool. They just said, I guess we can't do this, as opposed to actually thinking in. And that's just a good example of why thinking in data are complements and not substitutes, because big data doesn't mean you get to stop thinking. But yeah, we could talk for, we could keep giving many examples.
Yeah, there's a lot. I mean, I don't know if I can pick one either, but I think sort of two things come to mind now, and the first has to do with something I already mentioned in terms of the Lakens effect, but I think I want to focus on a particular piece of that, which I've noticed a lot, is this sort of obsession with accuracy. So now there's sort of a lot of classes have things like Kaggle, where you have these contests and you sort of want to make a prediction, and it means that you're essentially spending the entire final project teaching your students how to overfit. It's wild that people are not really focused on distinguishing between training data and testing data and sort of validation sets. And so I think that's one that I've noticed a lot now in the sort of big data space. And the other one I think is a little bit tangential, but I think it's worth sort of throwing out there, is this notion of emergence. And I think this is very related to things we think about now in terms of policy and the way that people behave. And so there's sort of a tendency to look at this big data set and sort of make overarching conclusions without thinking at all about sort of what the actual rules of the system and the structure are. And sometimes you do need to think about what the interaction rules are between agents in whatever system you're looking at, and can't just jump immediately to large-scale statistical conclusions.
Anything else on this?
It
Okay.
looks like maybe after all of that
I sent him a message because Matthew wanted to correct the not being big data, but being big error. And I just want him to specify a little bit more, because I want to make sure his question's answered. I don't know what direction to go in, because I was gonna do error analysis.
Let's do error.
Okay, so for me in high school, my favorite mistake is good old sampling bias. It is delicious. It takes a very long time to unlearn. It's painful because you'll stand right in front of them and tell them, here are some biased ways to gather data. And I'll say, oh, you want to make sure it's random. And they're like, okay, so if I go to a Cubs game and I stand outside and I ask them if they're Cubs fans, that's random. And I'm like, yeah, man, but aren't they going to be Cubs fans? Like, are you going to get a general idea? There's some Braves fans in there. Like, don't you think it's going to be a little biased? I love those. I love dismantling the sample bias. It is, I mean, they'll say, oh, I asked my friends, or I asked all my teachers and they said this, or I've always had math teachers that did this, or every math, it's always every, right? That's the only number students know is every. And so every single person that lives in Humboldt Park, or every single person in the South, or every single this, and just having them understand where they're getting their information from and how small that window is. And even back to the social media point, when they finally realize that their TikToks are so different. And it was weird because for my example, I just pulled it up. Like I had my TikTok up and I was like, have any of you seen this person? And they're like, no. I was like, yeah, because your information is small. It's very small. To get truth, it's coming from everywhere, right? So you have to be able to extend and find legitimate ways to gather intel from people so you can make those deductions.
So can I ask you to come over to my psychology colleagues who sample all their information from undergrads? Can you do this story, please? With the TikTok, can you come over? We need it. We need it, yeah.
Anytime.
In political science, there's a long tradition of experiments on Caltech undergraduates. Caltech was the place where people were studying these rational models of voting behavior. And so Caltech undergraduates were the big sample for a long time.
Okay, another question is, the choice of practical examples turns out to be immensely consequential, particularly at the high school or undergrad level. If all students see our social media data sets, they'll naturally assume that it's the only use of a method or the only career they consider. What topics do you think are underserved and could be given more exposure as practicums in data science education?
I'll jump in. Honestly, all of them are underserved because most of the time it's just a surface level touch through all the skills. And we're either hitting every single topic in statistics or in data science, or we're focusing on a few, right? So I think that all of them, every single one of them is underserved. And it also varies, right? Regionally, it varies by school, it varies by who's taking the class. And so that it's kind of tricky to figure out which one to choose, but it definitely relies on relies on the reader, right? It relies on the student, it relies on the learner to figure out which topics are more important than others.
Anyone else? No, Aditya.
Yeah, I think I mean I think this is an interesting question, and the sort of the thing that this immediately made me think of is for example, we teach signal and noise, and what's really funny about it is the first example of signal and noise is of course something like the cocktail party effect, where you can tune into somebody if you're at a crowded restaurant and sort of blur everybody out, and for the next 3 weeks all our students think is signal and noise only applies to sound, right? So I mean I think you're absolutely right that is important, and we spend a lot of time then showing them other examples of noise. As far as which topics I think are underserved, I think I second what Niki said, right? I mean, it feels like they're all very important. The one thing I was sort of curious about is, especially sort of high school early education, we noticed a lot of students come in with a slightly skewed understanding of what data is, and particularly to do with their own norms of what to expect, right? So I think we were talking about randomness, and one of the things that we see a lot of is students think that if you flip a coin a whole bunch of times, it should be heads and tails. And my favorite example, I think, one of my favorite examples in the course is what we call Fool the Professor game. So it's a very tangible physical example, and it works almost every time. You walk out of the room and you have the students flip a fake coin 100 times, and then that's literally, they come up with the sequence, and then they flip a real coin, and you can guess almost every time, because and it's funny because the fake one is usually some sort of heads tails. They're really scared about going past three in a row, and the real one of course has these long streaks, and so you just look for the streaks and you're like, okay, this is and I think that's the sort of thing that I worry a lot about, is these sort of expectations of what a statistical distribution looks like, without any real understanding. And I think if we could do something to sort of clear a little bit of these prior expectations, it might actually do a lot of good. Because I hate to say it, I've seen this in postdocs at Harvard as well, right? So this is not just an undergraduate or a high school thing. This is a very pervasive sort of thing with statistics.
I think the approach Niki mentioned of asking people in the beginning what they want to learn, I mean, that's a pretty good one, although they might not give very good answers, but content-wise, it might signal to things they find interesting. The problem I find with that approach is that looking for good examples is really super tough, and it takes a lot of time. So I sort of stick to my examples, and I already know my Facebook example is just outdated because it's true. I mean, I'm not on Facebook even. I'm already on TikTok, so they are on something else now. So that's a bit of a difficulty, and also a range of fields. I know stuff from my own background, of course, and my own interests. So that is reflected in choices that I make. It would be interesting to have a wider range of choices, good examples from a wider range of choices. I think it's a very good question. You would need to team up and create something like this. I don't have it. So yeah, I think it's a good point.
Yeah, and then the last thing I know with Skew the Script, we update it every year. And so we recently updated the COVID one and we updated the one on immigration. And so what we've started to do is kind of go with the flow of the times almost, and kind of like, well, what's hot, like what's going on, what are people trying to figure out right now, or what was recently figured out, or what's something that's kind of controversial where we don't know what side we're actually on. And so we'll take like those types of topics and then pull the math out of that.
I think that's very nice. You need a couple of people you trust to come up with good examples like that. And if you have them, then you can spread the load of coming up with this work, or distribute it. So yeah, that's a very good approach. But updating things every year, I have to be honest, I don't do that. I don't manage. Yeah.
I can't. It's all Dash. Dash he just takes off. I can fly by the seat of my pants with some lessons. Like one of them, I remember the most recent, we were watching the news the first 10 minutes and the insurrection happened. We were just watching the news. Like we were just having a day. And all of a sudden we were in class for 3 hours because we're all just watching, just like what is going on. And then from there, having mathematical conversations of like, where they get the information, like who said this, or this news channel is saying this, and that one's saying this one. And my students were like, here, let me show you what Fox is saying, or let me show what BBC is saying. And just like having them kind of investigate also helps change it for that next year, right? Like it's not so much a full, all right, take this and throw it out. It's like smaller things that as you keep teaching the same curriculum, that it's like, okay, now I know what I'm doing. So I know what I'm looking for, right? Like you always have the skeleton of it. You'll always have the framework. And it's crazy how like math minds can take that framework and just keep like swapping it in and out, because math is literally everywhere.
Okay, we have one question from our live audience here, and I'll repeat it.
Thank you. Can you hear us okay?
Okay.
Yep.
So as I'm listening to you talking about scientific reasoning, I keep thinking we cannot teach scientific reasoning without introducing scientific methods. And as I'm listening to the conversation, it feels like the way we look at the statistics as a discipline is, and I'm looking at data 8, data 100 content, the way we introduce a lot of the statistical concept is like we talk about average, we talk about the standard deviation. We kind of lack that cohesiveness. And when we look at the statistic and how it's so intertwined with scientific methods, introducing the scattered topics would defeat the true purpose of the statistics. Now, I know the origin of it is top-down approach and all that. I've set aside the historical racism that is in the origin of the statistics, but the statistics as a discipline cannot be taught without introducing scientific method. I think what we miss in the statistics education severely is introducing the scientific method. Enabling this, ask a question, form the question that you can answer by quantitative data, collect data or look at data set, analyze the data and draw a conclusion and communicate it. Not teaching them that method, that the skills in a statistics course is defeating the purpose of why we have a statistics. Like data is a wonderful course, but I'm looking at it and it feels like the statistics is used as a tool to introduce a lot of programming, which is a nice approach, but truly it should be the other way around. A statistics is introduced in a very inquiry-based path where we bring scientific methods by just 4 steps. Ask a question that we can answer by collecting data, look at the data, collect the data, analyze the data, draw a conclusion, and communicate. If we can, in those 4 frameworks, we can teach every single subject in the statistics, which means we have to change our mindset completely. Instead of throwing some idea and descriptive statistic right in the first chapter talk about me, we don't put it in the context, but then introducing the scientific method is defeat the purpose of statistics. But having those 4 steps, you can include every single thing. Sampling distribution, you can do it in those 4 steps. When we talk about random topics like p-value, with all due respect, that defeats the purpose of what p-value is. It kills me when I look at social science research program psychology work where they just use one p-value and they draw a huge conclusion without explaining where that p-value comes from. And that I asked actually a couple of the authors of the famous introductory stat course between p-value or test statistic, which one would you rather? And they were exactly the same. What do you mean, which one do I prefer? So without introducing that scientific method in our education, I think the purpose of a statistic is not to scatter not coincident topics where you bring the stuff and you through them. If you don't introduce scientific method in the past, you cannot connect pieces. And we do the speed up, of course, because they're like, what is this random ideas you're throwing at us and you're getting lost. So I was more of a comment than a question.
Yeah. So was everyone able to hear this, or?
I think I got most of it. Let me try to start, and maybe if other people want to ask some clarification or repeat some stuff. So first of all, I want to say I'm extremely sympathetic to this general idea, and I wouldn't just say that we need to teach the scientific method. I think we actually need to teach philosophy of science, because many of the differences, for example, Bayesian statistics versus frequentist statistics, you can't really understand what you're doing without a solid grounding in some philosophy of science. So I strongly, strongly believe that you should be teaching this. My experience is that people absolutely hate it. Like if they think anything is more boring than mathematics, it's philosophy. In general, that's just my experience. And even colleagues, I can't get them enthusiastic about these kind of things. So that's my experience. It's very difficult to do. I force it in anyway. So if you would, for example, see my course, Improving Your Statistical Inferences, there's one module that's about philosophy of science, and I do try to link to it. Even more, the second course that I taught is called Improving Your Statistical Questions. And I think it mirrors your same point. Like you can compute these statistics and that's all lovely, but actually you need to think, what is the question I'm asking? And there you can't do it without sort of, what's your goal? What's your philosophy basically? Or your, are you doing the scientific method? Are you trying to do falsification, for example? Like a large part there is saying, are you actually testing something? Or are you describing something? Or are you trying to predict something? Like those questions. In my field, people always test a hypothesis, but they don't really know why. Just because they think, well, I'm doing a master thesis, I should be doing a test of something, right? So explaining them that that's not the goal. Anyway, so I agree, but I think the challenge here is super difficult, and even fellow scientists like zone out when you start to talk about philosophy of science. It's also the reason, by the way, why Bayesians and frequentists have been debating stuff for the last 60 years, because nobody just wants to get down to the differences in philosophy of science. That's just where it comes down to, so, but nobody wants to talk about philosophy, so they keep debating.
Okay, we're at time, but let's finish this because I see Aditya and Anthony unmuted themselves. So let's hear what you want to say.
Yeah, no, Daniel, I agree completely. I think, the philosophy of science aspect is absolutely crucial. I want to just push back a little bit about the scientific method piece, because I think we have to be clear about what we mean by the scientific method. A lot of what we've sort of seen as concerning thinking practices come from the standard scientific method that you find in the beginning of sort of every middle school and high school textbook. That you have the hypothesis, you go out and do your experiment, and then you get results, and then you take that and you put it into the sort of labs that I think most people experience in high school, of where you already know the answer. And if you already know the answer or know what you're supposed to get, then it's building a really bad association with what I think the scientific method is really supposed to get at. And I don't know if we have anyone sort of from different backgrounds. I talked to one of our students who sort of came from a background of education in the French system, and he said, no, all of their experiments through high school were things that they didn't know the answer to. So maybe it's less relevant to sort of say, let's prove this thing that we just learned about in the textbook as a way of illustrating the scientific method. And more about getting at this notion of how science works. So like one of the concepts in the course we try to address, and it's a very flawed analogy, of course, is broadly this idea of a raft versus a pyramid, right? That science is this iterative process, and it's not this thing where you have a foundation, you build everything on top of it, but that we're all engaged in the process of discovering things. And especially if you have prominent professors talk about their experiences being wrong, and then sort of how they learned that they were wrong in something that they that they discovered, and that they didn't ruin their entire career because they made a mistake somewhere or had a wrong hypothesis. I think that's the spirit of scientific thinking and the scientific method that I'd like to imbue a little bit more than the you do this and you do this and you do this, and if you don't get the answer, you fudge your results and you get it anyway.
Yeah, I agree with everything Aditya and Daniel just said. I mean, of course, I think we should spend a lot of time in our classes talking about what's our goal, why are we doing this, and remind ourselves of that, and we need to match what we're doing to our goal. And so even if we don't have a specific module of our classes that's called philosophy of science, it's kind of constant throughout the courses. I would also agree with Aditya's comments that the scientific method is not so straightforward, and the way that we teach it to traditionally in high school and middle school is actually not very productive. It's a lot more complicated than that, and the actual scientific method is a constant interplay of theory and looking at evidence and making a guess, and then doing some more theory and looking at evidence again, and in all kinds of random orders. And that's just kind of how it works. And there's nothing wrong with that as long as you're honest about what you're doing. I think we've all seen lots of bad science where you find the crazy result, then you cook up the theory afterward, but you pretend that the theory came before, and you say, oh, look, I tested my theory. Obviously that's a irresponsible thing to do. And vice versa. We see I cook up my crazy theory and then I manipulate my data to get the result. Like, all of those things are bad. And so that's why we have to harp on this stuff, but there's no one right answer. And the way this stuff actually progresses scientifically is very complicated, and it's through some constant interplay, and it involves lots of people, and it involves criticism and rethinking and so forth. And so I think it would be a mistake to give students a very formulaic, algorithmic way of thinking, to say this is what the scientific method is like. I actually think that's one reason why some of these classes are so hard. When you teach, if you teach calculus or differential equations or intro mechanics or E&M, those are very easy relative to what we're talking about. Those, you can give students an algorithm to follow to answer all the questions they need to follow in those courses. And that is not true in the kinds of courses that we're talking about. There's no step-by-step instruction book to get the right answer. It's very complicated. You have to think about lots of things at once. You have to be willing to recognize lots of different problems. And it might be that you see a new problem that no one has ever thought about before, and you have to think through it yourself. So of course we should not ignore philosophy of science and ignore the scientific method, but it's very complicated, and that's why perhaps why we're reluctant to have a chapter of our books that says, here's the scientific method and here's how it works.
All right, then with that, we will wrap it up. Thank you so much. Niki, Daniel, Aditya, and Anthony. I'm sorry if we didn't get to some of the questions in the chat. I will take a look at them and see if we can address them afterwards. If you have questions about this, if this is something that interests you, email me at spatial@uchicago.edu, and we'd love to add you to what we hope will be a growing community who will be working on these topics. So thanks so much.
Awesome panel. Thanks, you guys. Really great. Really great.
See you
Great
soon.
job. Great job, everybody. This was fun.
Thanks so much, Julia and Eric, and thank you, Niki and Daniel and Anthony.
Yeah, for sure.
Thanks. Yeah,
Yeah.
nice.
Yep. Bye-bye.
Bye.
You can end it and it'll save the chat and I can email it to you.